Hello, good morning to this new lecture, and today's lecture has a very important topics. The topic is integral, so it is in the title of the lecture and also here, integrals. Okay, some foreword before starting with a mathematical theory of integrals. So the first thing I would like to tell you is the answer of a question which is a natural question after doing some analysis in the high school, and also a question that some of you drew me during the last question time. And the question is why studying integrals before derivatives. And to this question, it is linked another question, and is it possible to study integrals before derivatives? Okay, I will try to give you a preliminary answer, and then we will see whether these answers are true or false when developing the theory. So the first answer for me, it is more logical, more natural. Why? Why? Because integrals are the analytical solution to the problem of the areas. The problem of measuring the area. The problem of measuring the area of non-regular regions of the plane. This year in analysis 2, you will measure volumes in 3 dimensions and more than 3 dimensions too. And so this problem is extremely natural and extremely ancient. Already in the ancient Babylon, people were interested on how large were the fields, whether they were richer and they had a larger field than their neighbor. So this is a very ancient problem. So the problem of computing the area of irregular regions is already present in the scientific and pre-scientific literature of something like 5,000 years ago. So it is extremely natural, an extremely ancient problem. And on the other hand, the derivatives are linked, are the solution, the analytical solution, to the problem of the tangents, to the problem of finding the tangent line to a given curve at a point. So the problem will be the following. You have a curve, in particular the graph of a function, and if it is possible, you want to describe the tangent line at this curve at a given point, for instance, this point here, okay? And this is a much more specific problem, not so natural. It is a problem which comes, in some sense, inside the mathematics. It comes also inside the physics, but it does not come from everyday life. So it is a modern, more complicated and technical problem. So this is more natural from the point of view of logic. But not only of logic, also of the history. Second, so this is the first point. The second is also more logic from the point of view of the analysis and on the class of functions we are considering. Logical probably is the is the adjective. From the point of view of the analysis. Because in order to integrate a function, we will see what is the definition of integrating a function and of integrability of a function. But in order to integrate a function, you have to ask very few to the function. Only continuity, but even less continuity. One asks very few. For instance, so-called piecewise continuity, which means continuity except at a finite number of points. And it is too much. You could be more specific and ask much less than that. But let me stand here to piecewise continuity. And even less. In other words, integrable functions are a great lot. On the other hand, in order to differentiate, to take the derivative of a function, on the other hand, to differentiate a function, so here, to write down the tangent, to guarantee the existence of a tangent, one has to ask much more. One has to ask much more. And what is this much more? It's not only continuity, but something more, a certain regularity. Continuity is not sufficient. For instance, you cannot afford corners. Like this. If you consider, for instance, the absolute value of x is a function, this function exhibits a corner here. And here there is continuity, it is continuous, but it has no tangent. So no derivative. What do I mean with this statement? I mean that differentiable functions are very few with respect to integrable functions. So going from integrals, so from integration theory, to differential calculus, from integration to differentiation, means moving in the direction of smoother and smoother functions. And this is more logical than going in the direction of rougher and rougher functions. So we introduce tools and instruments that apply to an ever and ever restricted class of function. This is the idea that I find more logical from the point of view of the analysis. And in my opinion, it is also better from the pedagogical point of view. Why? Why? Because otherwise you learn strange things. For instance, you learn that integration is the contrary of differentiation. And it is not true. Simply, it is not true. Two different problems, computing the areas for integration and computing the tangent for differentiation. So, for instance, first, integration is not the opposite of differentiation. And second, which is important too, integration is difficult. Differentiation is easy. It's hard. Integration is hard. Differentiation is easy. So I prefer to introduce integration before. First, so we have more time. So we have from here up to the end of January to understand integration, which is harder, and 1 month less to understand differentiation. So is easy. It's not only easy, even less than easy, it's algorithmic. It is so stupid that it is an algorithm. A basic computer can do it. Okay? Integrating is not an algorithm. Integrating is really hard. So, okay, we will not go very deep into this motivation, but they are there. But the important point, very important point, however, integration and differentiation are linked together, are very strictly linked together. In particular, integration of a wide class of functions will be possible only after knowing differentiation. In differentiation. So derivatives. And I will introduce derivatives as a tool to compute integrals. Okay, this is not very historical because I will basically ignore the problem of the tangent. So I will tell you how to find the tangent of a given curve at a given point and so. But I will neglect the problem of the tangent as a motivation for developing derivatives, and indeed the true problem would be the kinematics of particles, would be the mechanics by Newton. I will touch a bit it, but not so close, and I will just let the idea of derivative come up naturally from the idea of integral. This is my line. Of course, I really don't want to convince you that this is the best line, objectively the best line. I found it much better and much faster than the other line. And it's not me who invented that. It's not me, of course. And the book by Enrico Giusti, first edition. Sorry, Enrico Giusti. I don't know if it is available in English, but it is a very beautiful and very deep book, quite difficult. And so it is Analisi Matematica 1. At least at the first edition it was like that. The new editions, I don't know, because then the world went to progressive simplification of everything and trivialization of everything. So probably the subsequent editions of Giusti abandoned this way. And another very beautiful book about that, and very short but deep book, was the book by Francaviglia, Sebastiano Francaviglia. It's a book on analisi matematica. And there are many others now, I don't remember. Okay? So let us start with mathematics. This was a foreword for you, and now let us start with mathematics. And okay, what is the problem of the areas? Very roughly, the problem is the following. You have a region of the plane, like before. You want to compute the area, and of course you don't know how to compute it, because you just know how to do with regular polygons and some other easy structures, and other easy regions. But here the region is completely arbitrary. Then you can simply divide it in many other regions of simple and regular polygons. The problem arises when you go towards the frontier, like here, because if, for instance, the region here is curved, then you don't know what to do. And a simple idea is to consider a lot of small triangles in order to roughly cover all the area, but then when you magnify, you see that there are other areas that are not covered, and so on and so on. So you keep on drawing triangles and so on and so on, but you really never get exactly up to the area. So the rough idea, the naive idea, is cover the area with many triangles, because you know how to compute the area of a triangle, but you discover very rapidly that one needs infinitely many triangles. And the problem is how to sum up infinitely many areas. And here one could go on for many minutes and hours talking about this problem from the historical point of view, not only from the historical point of view, and so on and so on. The main problem is that the human beings are finite, so we don't have an infinite time in order to perform a computation, so at some point we must stop. So the problem is how and when to stop the process in order to have the possibility to be able to conclude the computation in a finite time. And this is the problem. The problem now can be figured out in terms of a computing machine, in terms of a computer. But it was very clear in ancient times, and the first who gave a solution, not only posed the problem, but he really gave a solution, was Archimedes from Syracuse. So he was a Sicilian guy. In the 4th century before Christ, okay? In my opinion, Archimedes is the most important mathematician in the whole history, and he was a very deep scientist. And with Eudosso was before him, they invented the exhaustion method. Which is a forerunner of the integral calculus. According to some historian of the ancient science, it is completely equivalent to the integral calculus. And it was without derivatives. They invented the computation of the area, so roughly speaking, they invented integrals, but they did not need derivatives. Okay? And if you want to read a bit about that, there are many interesting books. One book is now, in Italian, it is Metodo, Archimedes. And there is very nice introduction by Acerbi to this book. And if you are interested in this problem, and with many links to modern theoretical physics, and it is extremely interesting. So the problem here is how to stop the process in order to be able to conclude the computation in a finite time, because we are finite. At some point we have to die, and since we have to die, we have to conclude our computations in a finite time. This is the main point. So in some sense, you can say the mathematical analysis comes from the fact that we are mortal, and without the death, we would not have a mathematical analysis. So this is a nice point in favor of death. But so not only that, let me be a bit ironically philosophical by saying that so in this sense, mathematical analysis, and in particular integrals, are one of the infinitely many aspects of the fight between man and death, man and infinity, and probably this is the only fight, or one of the few fights that we eventually win. I don't know whether eventually, and so on. However, let me be less philosophical, but the key of the solution, so the key idea of the solution to this problem use the tool of the analysis. In particular, two very simple tool that are supremum and infimum. Use the tools of the analysis in order to be able to stop the computation at a finite time. This is what we will do. In this part of integral, when introducing derivatives, we will also use the limit that directly comes from ideas like supremum and infimum. This is the key idea, but we won't be able, after analysis 1, we won't be really able to compute the area of an arbitrary region in the plane. The only region in the plane will be the region below the graph of a function. So we'll focus on areas or regions that lie below the graph of a function. Below or above, it depends on the sign of the function. In particular, the areas we will be able to compute are the following. We will give you a function f whose graph is something like that. So we have an area here and another area here. So here we will compute the area with a plus sign of a positive function and the area with a minus sign. Okay? This is what is called in some books like area with sign, and it is not a so clever way of speaking because the area always has a sign. In general, it is positive. But however, it gives you the idea. You could also end up with negative areas. This means that the function will be below 0, will be negative, the graph will be below the x-axis. Okay, but we will start to see these features and others in the next video.